Oh, right next to it.
Okay, I think we can go ahead and get started. So it's my pleasure to introduce Professor Antonella Palmese. How do you say your last name?
Yeah, perfect.
Okay, perfect.
I go with Palmese in the US.
So Antonella is a professor at Carnegie Mellon University. And before that, she was an Einstein Fellow at Berkeley. And before that, she was a postdoc at Fermilab and got her PhD at UCL. And Antonella is an expert on multi-messenger astronomy, and so she'll be telling us today about probing the universe's expansion with multi-messenger astronomy.
Thank you so much, everyone, for coming to my talk today. So I'll be telling you about measuring the Hubble constant and also more broadly about multi-messenger astronomy, but by multi-messenger here I mean with the use of gravitational wave data and mostly optical electromagnetic data. So let's see if this works. So first I'll start by telling you about bright thunder sirens and what we're currently doing to follow up gravitational wave events in the 04 observing run. For those who don't know, this is the fourth LIGO-Virgo-Praga observing run that started last year now. It should be ending in February next year. And then I'll move on to telling you about things that don't have electromagnetic counterparts and that we use as dark thunder sirens, and specifically work on the case where we use galaxies in order to make a Hubble constant measurement. And then at last, I'll tell you about one formation channel for binary black holes and how we can also use that specific case of binary black holes merging in the distance of AGNs to do cosmology. And here's a couple of acronyms. Sorry, they're a bit small for people in the back, but I'm sure many of you are aware. But if you see my slides, BNS, binary neutral stars, BBH are binary black holes, DCAM is a dark energy camera, LDK, LIGO-Virgo-Praga. So what are the gravitational waves that I'm considering here? This is a picture that many of you have probably seen a million times by now. Hopefully we'll get an update very soon. So this is all the binary black holes, the neutral star black holes, and binary neutral star mergers that have been detected by LIGO-Virgo-Praga up to the previous observing run, 03. On the y-axis you have the mass of the objects. So as you can see, we're talking about stellar mass binary black holes and neutral stars, so we're not talking about LISA kind of gravitational wave events in this talk. So in blue you see most of the events are black holes. You have two objects, and the row points to the mass of the remnant object that is formed with the merger. And then you have a couple of objects that are in orange, and these are the neutron stars. So these are the objects that we'll consider here. On the electromagnetic wave side, the instruments that I'm focusing on here are the Dark Energy Survey, or DES. So this is actually the survey for which we took images of galaxies, and DCAM is the Dark Energy Camera. So DES was about 6-year program that ended in 2019. We had a wide survey program that covered about 5,000 square degrees of the southern sky, or this tank-shaped footprints that you see here. So that translates into more or less high signal to noise measurements for 300 million galaxies in GRIZ bands for the most part. We have a lot of public data that you can access at this link, and you can always ask me questions if you have any. So this covered most of this, pretty much all of the region, and we also have value-added catalogs that count for the first 3 years of observations, with more coming up soon. DCAM, the Dark Energy Camera, was the instrument that was built to carry out the Dark Energy Survey. This is a camera that's actually still mounted on a 4-meter telescope, the Blanco telescope in Chile. And even though DES is over, we're still using the Dark Energy Camera to perform gravitational wave follow-up, amongst other things. And it's still a great instrument, as I'll show you a little bit later, to do this kind of follow-up. One of the reasons it has a decently large field of view. I'm sure many of you here are aware of the upcoming Rubin Observatory that will have an even larger field of view. It will be mounted on a larger telescope. But for what we currently have, this is still a great instrument to chase kilonovae objects. So On the spectroscopic side, I'll be talking a little bit about results using DESI or DESI data more broadly. So DESI is a dark energy spectroscopic instrument. This is a 5,000 fiber spectrograph, also mounted on a 4-meter telescope, but it is a Maillard telescope in Arizona at Kitt Peak. The field of view is also pretty large, so that's nice to do for long gravitational wave events. We have about 8 square degree field of view in this case. The goal of the survey that is being carried out with this instrument is to survey about 14,000 square degrees of the sky, take redshift for over 40 million galaxies. And so we're on good track to actually achieve that pretty soon. So we started taking data in early 2020. Actually, this should be updated. Well, we finished taking year 3 data. We were pretty much ahead of schedule, but that's recently had a failure, unfortunately. So we'll see. Hopefully, we don't fall back in the end. In terms of what I'll use in this talk, I'll be focusing a lot on the DESI imaging data. So this is what we call the legacy survey, especially for the dark side results, because this is what we had available at the time. You know, we're still working on the cosmology results on the cosmology catalogs from DESI on a broad region of the sky. We currently have released, probably you heard about the year 1 release, but that covers pretty much mostly a stripe, an equatorial stripe over the entire footprint. But we'll be giving you more results also using DESI data soon. And so the DESI imaging survey was the photometry that we took in order to define which targets we would want to observe spectroscopically. So this was GRZ observations, also using the dark energy camera in part, plus WISE infrared bands to define the targets and also get photometric redshifts. And here's just a press release now from last year, just to give you an idea of how exciting it is to be in DESI. Right? So this was, well, actually, 2022 is 2 years ago. Right? At the time, that's when already DESI had taken more galaxy spectra than all previous spectroscopic surveys put together, and that was 2 years ago. So we're really, it's a really exciting time to be involved in this experiment. Now we want to combine radiation waves and these electromagnetic wave observations to address the Hubble constant tension without taking too long. I'm sure people here are aware there's a 4 to 6 sigma discrepancy between Hubble constant measurements coming from early time universe measurements, mostly from the cosmic microwave background within a flat lambda CDM scenario, and Cepheid anchored supernovae type 1a. So this is where the highest discrepancy occurs between these two specific measurements. Here's a nice compilation from Leonora Di Valentino a couple of years ago. Things haven't changed really much, but if we want to understand where these discrepancies arising from, if we want to get an independent measurement of the Hubble constant, ideally if that's coming from the late time universe, like the gravitational waves that we saw earlier, then ideally we want that to be independent of the same sets of systematics that might be relevant for the Cepheid anchored supernova type 1a measurements. So indeed, independent of the distance ladder for the most part that is used in the supernova. Standard science do offer that possibility, right? We can get a luminosity distance measurement directly from the gravitational wave experiment, and then if one is able to identify, for example, the host galaxy, you can get a redshift of it. You get multiple events, hopefully someday, then you can start populating this Hubble diagram and measure the distance redshift relation, which is in turn sensitive to H0, at least at the lowest redshifts that we'll consider here. So there's different kinds of standard sirens. So the bright standard sirens, so they all differ pretty much based on where the redshift information on that x-axis is coming from. So for bright standard sirens, that's hopefully the case, at least for a good fraction of neutron stars and some neutron star black holes for which we can find electromagnetic counterpart. Now the redshift is coming from a unique host galaxy. And in the case in which we don't have an electromagnetic counterpart, we can take into account all of the potential host galaxies that fall within the localization volume that we get from the gravitational waves. And then in the third case, in which we don't want to use galaxies, or perhaps the localizations are too large, right? Especially the LIGO-Virgo collaboration has been focusing on getting this measurement even just using gravitational waves alone a method that is called spectral science. So here the information is coming from the redshifted mass. So if we can assume something about the mass distribution, then one can infer something about the redshift and get a an H-naught measurement that way. But I will not be focusing on this third one. I'll just be focusing on the two that are truly multi-messenger, where we need these optical data that I mentioned earlier. So for the first case, right, we want to make a first standard star measurement, we need to find counterparts. So for binary neutral star mergers, the types of counterparts that we expect is possibly a jet, especially if you're aligned along the axis of this binary. And so this is what you see in the video in gamma rays. In magenta, so hopefully something that we can see in gamma rays. Then you see also this ejecta expanding in violet and in white to red. This is the ejecta that we expect from the kilonova that is hopefully visible across UV to optical to the infrared. And then also an afterglow could be observed, also an afterglow of the jet interacting with the circumstellar medium, but potentially also an afterglow coming from the kilonova, something that has been proposed also with previous observations of GW17 and hopefully that's something that we can observe across X-rays to optical to radio. Now I will claim that the kilonova is what I mostly look for because at least for cosmology, it's what could be the most promising counterpart, at least at the current detector, within the current detector's horizon. Right, this is an isotropic thermal transient that is coming from the radioactive decay of the heavy elements that are produced in the ejecta. And it's, as you could see from the video, it's kind of isotropic for the most part. So we can hope to see it from different angles. So we can hope to see more of this kind of counterparts compared to what you can see in terms of jet and jet afterglow. So you need to be aligned with the direction of the jet in that case. So hopefully you can get more precise statistical constraints on H-naught if we find more of these things. But I'll also show you what happens when we can see the afterglow. So it was, for the case of 17817, was the fact that we were able to identify the kilonova that allowed us to pinpoint precisely where the merger actually happened. And so this led to the first measurement, standard star measurement of the Hubble constant in this paper led by the LIGO-Virgo collaboration. So the posterior is what you see that was gotten from that measurement is what you see here in blue. And the vertical blue lines show you the 1 and 2 sigma constraint, and you can see how they compare with what we had at the time from the CMB measurements here in green, and the supernova measurements from 2017 at least in orange. So obviously the constraints from this one event are much broader and are consistent with both early and late time measurements of the Hubble constant. That's expected, because obviously it's just one event. But in the future, it will be very interesting to see what we get from standard science and how they compare with these other measurements. One, because this, as I mentioned earlier, we don't need a distance ladder to calibrate the distance of the gravitational wave events. And also because these measurements being so nearby, they're cosmological model independent. So we're not making an assumption about we have a flat lambda CDM scenario, as it's the case, for example, in the Planck measurements that we're showing there. So now some limitations that we need to take into account. One is the peculiar velocity of the host galaxy, right? So if you're trying to use the redshift of the galaxy to infer the Hubble expansion, you need to take into account the fact that the galaxy is also moving to the local, due to the local dynamics, and you need to subtract out that contribution from the redshift that you observe. And also the inclination angle of the binary is correlated, is degenerate with the luminosity distance, which translates into a degeneracy between the inclination angle here on the y-axis and the Hubble constant. So that you see even these contours here being very degenerate, meaning that a lot of that uncertainty that we see here is actually coming from this degeneracy with the inclination angle. So if we can learn something about the viewing angle, for example, because we see the jet or we see the afterglow, right? It means that we're kind of at least somewhat on axis, and so we can use that information to improve our precision on the Hubble constant.
Question. So you're going to go into this then. You're going to explain to us how accurately the inclination is actually measured in the slant?
Yeah, yes, okay, that's right. Yeah. Or at least what we have done, there's different measurements that use different techniques, I should say, that I'm not covering here. But yeah,
But before you get into that,
Yeah.
So this has an NGC number, this galaxy. So is it in a group?
yes.
And roughly, what is the imperial speed of galaxies in that group? Well, what is the error from that?
I can give you, there is another slide where you can actually see a little bit more of that. But do you want to know okay, well, we'll discuss when we get to that word. But yeah, so on the specific of the inclination angle, what we did was using the afterglow data out to 3.5 years after the event. This was a very long-lived afterglow because it was on off-axis. So, a lot of the short GRBs that people have observed afterglows for without the gravitational wave events, typically they are more on-axis, so they decline very fast, versus most of the gravitational wave events that we expect to see follow this Schutz distribution that peaks around 30 degrees, and so that's why the afterglow actually looks quite different. So in this case as well, that's what we believe actually, that the constraint on the viewing angle was close to 30 degrees. So what we did was using this hydrodynamic simulation-based code developed by people at NYU, and to model the observations that we had all the way from the X-ray to the radio. So these are the light curves of wax function of time, in the X-ray to the optical to the two radio bands to get an inference on the viewing angle. And so here you see how we're able to break the degeneracy between the gravitational wave data. This is 90% counter, and then the afterglow gives us a nice constraint on the viewing angle, and we can combine these two to get this precise measurement on the viewing angle, at least based on the afterglow observations. There have been other measurements, for example, using the kilonova. I think the uncertainty is more like 10 degrees, if you believe that you can model kilonova.
So the argument here is, of course, famously, GRB jets are thought to be structured. The argument here is that the viewing angle is large enough that you sort of have forgotten about what the detailed structure of the jet is, and you're just following the asymptotic spreading of the jet.
That's right, yes.
And so in the simulations in which this is based, I mean, obviously you can't try every initial condition, but was there some attempt to try different initial jet profiles and see what range of profiles would fit the data? Or?
Yeah, so my understanding as an observer of this simulations is that they are able to reproduce the different kinds of outflows, structures and properties. So in some sense, we are marginalizing over the structure of the jet in this case. And I'll highlight that all of this work was done by Brabka, which is an undergraduate at UC Berkeley. And these are the constraints that we get. So also taking into account the peculiar velocity, which we might get back in a couple of slides. And the final posterior that we get is the one that you see here in black, with the value reported here, and this is about a 7% H0 precision, which you can compare with the first measurement of the Hubble constant that I showed before, which is about 14%, the 2017 measurement that you see in this plot in dark orange. Although really what we used was this other result from Nicolau et al. 2019 in light orange, so actually our constraints get even better if you compare it to that one, where we're taking into account in a different way the peculiar velocities compared to what was done in the 2017 paper, where we are saying, well, we can use different radii to consider the peculiar velocity around NGC 4993, considering more or less galaxies, because we don't know exactly which is the radius of that group of the galaxy. At least we didn't know back then. So it's a little bit more conservative than the 2017 analysis. Okay, so what are we doing now to find more of these things? Because we're all tired to talk about GW17 or 817. So this is a GW MATS. I want to introduce this as a radiation wave multi-messenger astronomy GCAM survey. Here's a few of the people involved, especially graduate students and postdocs at CMU, and Igor Andreoni is the co-PI from Maryland with myself. And then we have a lot of collaborators, so including people from the CTF team with whom we're coordinating observations, as well as a group in Germany at LMU, and also people working on the AGN disks formation that I'll mention later. So this is a survey program, NSF NORI survey program that will run until the end of 2004. Overall, it has about 25 full nights of target opportunity, which we hope we'll be able to use more during the 04B rounds. For those who don't know, the first part of 04 ended in January. We just started running the second part. What we do is we try to process the data as fast as possible. We have a GPU-enabled difference imaging pipeline that was developed by our postdoc, Lei Wu. And we try to report as soon as possible, ideally within, that's what we've been doing, within 24 hours from the time we take the useful information, as in there's no cloud, observations have templates. We report between 24 hours to the gamma ray coordinate network and also to the transient name server. So here I'm just showing an example of a follow-up that we did in September. This was a binary black hole event. We follow up all sorts of events, not just binary neutral star mergers. Also neutral star black holes, binary black holes, especially those that could be more massive and originate in the disk of AGN. And potentially, if we get one, if we get a strongly lensed event or candidate, we will try to follow that up as well. So in this case, we heard about 70% of the sky map of the probability area that corresponds about 200 square degrees. And we so here you see how the Carnegie camera pointings are even in black, how we cover most of the high probability region for this event. It is given by the orange part. We found over 1,000 astrogalactic transients that we try to filter out based on redshifts and other things. And then we coordinate with other instruments for follow-up, both ground-based and space-based. So here's a quick slide on what we expect to see. So here, my student, Karthik Vanunkai, she ran end-to-end simulations using the Amanda Farras distribution of compact object mergers from GWTC3 from the last, considering gravitational wave events from up to the last observing run. And also then we use kilonova models from Bulla, and what we recover here is showing you the total mass versus distance of the events that we have recovered that we believe will be detected for binary neutral star mergers and neutral star black hole mergers. And then you can pretty much just focus on the blue histograms and the blue points. Those are the kilonovae that we simulate, and the things that have a red point or a black point are the things that we detect. So this is about 70% of the binary neutral star mergers we believe we should be able to detect as long as they're observable with our telescope, given our fiducial depth. This work was actually used also to say what is the optimal depth actually that we should consider for a given binary neutral star or neutral star black hole merger given its distance. And this is a case of neutral star black holes. So most of the things are in yellow because they don't produce a kilonova, but you can see that some of them are because our mass gap between 3 and 5 solar masses is not empty using Amanda simulations. So we are able to detect something that looks like 8% of the NSPH that we can detect in gravitational waves, as well as about 70% of binary neutral star mergers. So if we get a binary neutral star mergers and perhaps not very symmetric mass neutral star black hole, hopefully we can actually find the counterpart. And a few words about what we're doing with DESI.
Before you go on, you quickly went past this amazing number of 1,000 transients that you were determining were background and had nothing to do. How many did you have to look at carefully because they were varying rapidly enough that you couldn't be sure without follow-up?
Yeah, so that's a good point. So specifically for this case, this was a binary black hole merger.
Yeah.
at least for what we're looking for, we request more than one observation. Well, in general, we request more than one detection because, we want to reject asteroids. So if you just get one detection, then the thing moves, and you.
What fraction of those 1,000 were extragalactic?
I think as we get to 1,000, it's pretty much most, but like we have also a lot of AGN variability that's just in there. But if we were looking for a kilonova, we would be looking for something that is declining very fast.
I mean, people have sometimes thrown out the idea that finding black holes could somehow produce an electromagnetic transit by an electromagnetic instability, and so, if that happened to be the case, I don't think many people take that seriously. That would mean a relativistic shock. So, I mean, were any of those transients potentially consistent with, the relativistic shock that was producing the primary neutron star transient?
The relativistic shock that was causing.
Well, in the double neutron star case, you had this beautiful forward shock synchrotron emission. I think it's basically what it was, right? Light curve. And I mean, how many of the 1,000 transients were at first sight potentially consistent with that type of process? Just a relativistic shock.
Yeah, I don't think that we had any there. Okay. Again, we focused on just looking at the nuclear things because, as I'll say later, we were focusing on the AGN formation channel.
Okay, so you were looking for potential like explosions in the center of the galaxy.
Delayed. Yeah, and delayed flare, yes.
So when you say transients, you mean things that were associated with the centers of galaxies, basically?
No, in that, the 1,000 is anything.
Anything.
But then we also cross-match with galaxy catalog, so we exclude a lot of things based on the redshift. Especially if in a lot of these cases we have DESI redshifts, and really that helps a lot to have DESI redshifts.
And the time which you covered the error alerts was what a week?
No, so that was about 4 hours, 200 square degrees. Obviously, it depends on the depth that you choose. But yeah, so our target is typically 4 hours.
So that'll be the sort of characteristic follow-up.
Yes. But yeah, we typically, if we're looking for kilonova, what we do is we go in one band and then we come back so that we actually do find the very fast things that you were mentioning. But we didn't do it in that case because that was a binary black hole. So I don't have a number of very fast transients in that case because one detection we just reject.
And sorry, but what upper limit are you setting on the energy and EM from the binary black hole compared to gravity waves?
So in the energy from the EM emission.
If one just posits, okay, this event could produce an electromagnetic transient. I guess it would have to be a shock because you're not going to be seeing it immediately, on the same time scale as the gravity waves. But, if you had some sort of explosion associated with the binary black hole merger, can you set an upper limit on what the energy carried in that would be compared with the mass energy released by the merger?
Yeah, so you can try to estimate some energy based on, depending on which mechanism you think produced that transient. But are you saying upper limit because you don't know?
I'm just wondering,
you don't
it's a very
see it.
Model agnostic way.
Yeah, I think the difficulty there is that that energy would depend on so many parameters. At least, okay, so again, we're focusing on the AGN case. Mm-hmm. So you have where exactly is it happening in the disk? How high the disk is, and all of this.
Emissivity will depend on that. Yeah.
So you could have a range of possible energies that you could use constraints on, but that would be very uncertain based on this.
Okay, sorry. Thank you.
So on the DESI case, would kind of follow up are we thinking about. So DESI would the way we will contribute is through a quick classification of all this 1,000 candidates that we find, right? So here we have 5,005 years. Obviously, we don't use all 5,000 to look at objects, but about 3,000 typically we point to galaxies and also potentially transients. So if you're able to point DESI to these regions, you could get the spectra of all of these objects. It would be super useful, especially for the AGN case. Because you can get, all the AGNs perhaps in the area at once, maybe at the beginning, and then you can look at that later as well and see whether you see some changes in the broad line region, for example. So here's an example. What we did, this was a simple dry run because we were not online at the time of 03, but we did it after also to get more galaxies, to get redshifts for dark side analysis. So this was GW190412 was a well-localized event from 03, and we were able to probably just do nice DESI pointings that you see here in red. So we were able to get thousands of galaxies in that region. At the same time, just having the DESI redshifts helps us so much, as I mentioned earlier, to guess which ones are the transits or which ones are the galaxies that could be at a redshift that is consistent with the gravitational wave event. And so we're doing also what we would like to do. We have done it for one event from last year that was S230627C, where we had coverage by DESI and also decently levelized event. And so we just go and do a targeted search with other instruments, not with the Carnegie camera, because that's wider field. We don't need to do targeted searches. But for example, with this 2-meter telescope in Germany, we work together with the LMU team to search for transients around those promising galaxies. And also we're mapping the environment around events for cosmology. So as I was mentioning earlier, the peculiar velocity of this of bright sun sirens is very important for the cosmology measurement. So this is what we did around GW170817, the one event with the counterpart. And so this is maybe what you were asking before. So this is the velocity along the line of sight subtracted by the velocity along the line of sight of what we believe could be the BCG. I think until this point we were not really sure about the halo and the group of galaxies around NGC 4993. So this was very helpful observations that we got with DESI last year, and we're still working on getting new data on this region this year. But so here you can see the velocity dispersion for different halo masses given by these different lines that you see here. We believe this is possibly something between 10 to the 13 and 10 to the 14 solar mass halo. We got observations also of peculiar velocity targets, so Talley-Fisher fundamental plane galaxies, to get more, a better measurement of the peculiar velocity of this group just by observing more of the galaxies that give us that peculiar velocity measurement. So this is a way that DESI will contribute hopefully in the future to standard sirens as well. So where are we headed to in terms of bright standard siren measurements? I think Maya maybe can tell you better me, since she was in this original paper by Qinyu Chen and also Dan Holt, where they first came up with this number that you need about 50 events, I think, to do a 2% measurement of the Hubble constant, and that's what you really need to discern between these early time measurements and late time universe measurements of the Hubble constant. So here's a perhaps newer version of what we can achieve. So in terms of H0 precision as a function of number of events combined. And so if this is the orange line, just tells us if we start with something like GW170817, this thing will arrive at about 2% after 50 events. But if we're able to include some information about the viewing angle, for example, from the afterglow or from the kilonova, in this case, I'm assuming a constraint that is similar to that was achieved or claimed at least for the kilonova, about 10 degrees precision on the viewing angle, then you can beat down the uncertainties from the orange to the blue line and hope to get to that 2% with a dozen events. So hopefully that's something we can achieve, I believe, at this point in 05. Initially, we believed we could have achieved that in 04. So this is a nice old now prediction, but okay, 04 is not over, so let's see what happens. But I believe we'll be in 05. So moving on to things that don't have electromagnetic counterparts. Here I'm just showing you some very simple simulations to show more or less how dark sun of science works. So here's a dark energy survey-like galaxy simulation on which we simulated very simple gravitational wave events, assuming an h0 of 70 kilometers per second per megaparsecs. And here you see the h0 posteriors for the single events, given by these gray lines that you probably can't see, but you can see a few that are in color. So you'll see that for a single event, there are potentially multiple peaks in the h0 distribution, posterior distribution, and that's totally expected because if you have one galaxy, it's one redshift, and one luminosity distance from the gravitational event, you expect to only have one peak in the h0 distribution. But if you have multiple galaxies or multiple overdensities along that line of sight, that for a given luminosity distance, that will correspond to different values of the Hubble constant. And so that's what you're seeing there. But as you combine more and more events, the idea is that there will always be support for h0 around the value that you have injected. Right? So there should always be, at least in the simple simulation, there should always be a galaxy there. So eventually, as you combine hundreds of these events, you can get a posterior that is shown here in this case in black that is giving us a nice constraint around the input value of the Hubble constant. And what you see going from the top to the bottom panel is just increasing uncertainties on the luminosity distance and on the redshift. But what that tells us is that as we go to realistic cases from 1 or even 5 events, you don't get a very precise constraint on the Hubble constant. You need to combine hundreds. So where do we stand in that regard? So here I'm showing you some work that we did using the previous observing run 03 events. So again, in 03 we had more than 50 gravitational alerts, but there were no high confidence counterparts, so that's why we're doing this kind of measurement after GW17 And what we did here is only considering well-localized events that fall on high completeness galaxy catalog, which is the DESI imaging that I mentioned earlier, and the footprint of the catalog is what you see here in light orange, and the events that we take into account have a 50 and 90% credible interval shown here in the different colors. And what we find is a H0 posterior given here by the blue line, and combined with GW17 with 17, we get the constraint in black with the value that you see reported in the slide. So adding on this dark sirens, this well-localized dark sirens improves by about 30% the precision of the GW17 with 17. So it starts to be an interesting addition to the bright standard siren, given the low rates of the bright standard sirens. A few systematics that we have been taking into account in my group or in other works, also including Maya and other people. So in my case, I focused a lot on the photometric redshift systematics. So what we did, for example, is try to understand like the biases that we have in our photometric redshift estimation using a controlled sample. So sample where we have a lot of spectroscopic redshifts that we can trust, and try to see how our photometric redshift estimations perform. So this is what we're doing here, like trying to measure the bias as a function of the photometric redshift that we can include in our posterior, marginalizing over the value of this bias. Now, obviously, this does not really matter if we have spectroscopic redshift. So as a proof of principle with an undergrad at CMU with Ballard, we tried this with the one well-localized event that I showed you earlier that we did the dry run on, GW190412. So this is what we get. We can focus on the purple line here is a very broad constraint on the Hubble constant in this case. But this was a nice proof of principle to understand also how to use the large-scale structure catalogs and the weights that come with the DESI cosmology analysis, and how to fold them into the dark standard siren measurements. There's more to redshifts. There's also gravitational wave selection effects that need to be taken into account. Completeness of your galaxy catalog, which people have done in different ways, including again our weights in the DESI catalogs, or correcting for that incompleteness in different ways. For example, Rachel Gray has done a lot of work with that, other than Maya. And the next, I think, big thing will be to look into the expectations of the effect of different binary black hole formation channels that will happen in different kinds of galaxies that will be probably different from the tracers that we use in our measurements. And so we need to see how that affects our H0 measurement. I think I will probably skip this part and move on to the last part of my talk, which goes back to the initial graveyard of binary black holes. And so focusing on specifically the upper mass gap, which is this region perhaps between around maybe 45, 50, 55, up to 120 or so solar masses, where we don't expect to see black holes simply because of the isolated formation channel, because there is pulsational parent stability supernova and parent stability supernova that should prevent the formation of these objects in this region. Also because the radiation wave population analysis seem to indicate that there is there are different formation channels at play, that not the entire gravitational wave population is coming from one formation channel. I think it's interesting to explore possibilities beyond the isolated binary scenario. And here I'm focusing on the one where binary black holes might form in the disks of AGNs. So this is a great environment for the more massive stellar black holes that LIGO is observing through repeated mergers of stellar black holes in AGN disks. So unlike perhaps globular clusters, you can retain them more easily after they get kicked, just because you have a stronger gravitational potential. But I'm also interested in this because you can hope to get an electromagnetic counterpart if these objects are embedded in gas, perhaps. And there was an indication that this might have happened, at least for some events, in the last observing run in 03, because the ZTF team in particular, in this work led by Matthew Graham, they found up to 7 AGN flares in coincident with radiation wave events, with the most famous one being coincident with GW190521, which had both component masses fall within the upper mass gap. So this is especially interesting, and here you see the flare, the AGN flare that they found in GNR band. You see after the gravitational wave event, there was a delayed flare that happened, that was observed, that was significant compared to the previous AGN activity. So this is what I learned so far from the theories. There's a couple of different ways in which you can make a binary black hole electromagnetic counterpart. So imagine you have this binary embedded in the disk. Potentially you might have something that they call run pressure stripping of the Hill sphere that is bound to the remnant. So basically the idea is that there could have been some gas that was bound to the binary before it merged, and then as it merges and it's shocked, and it's kicked, the remnant is kicked through the AGN disk, this sphere of gas will try to follow the remnant and will collide with the gas in the disk. The other possibility is that you might have just a Bondi tail, so some drag that is coming from the gas around the kicked remnant, and that drags it and also accretes onto the black hole. This is what was actually used to explain the flares that I mentioned in the previous slide. But then people started coming up with other possibilities. You might imagine that maybe you had a binary that was already launching a jet, so the jet actually opened a hole around the binary, but as it merges, the jet is reoriented with the remnant, and so it might actually end up causing shocks with the gas of the disk, and maybe you might be able to see some shock breakout emission from that. And they were also able to explain those flares from the Swedish tungsten facility using this model. And another thing that we discussed earlier, where you might have a jet afterglow, that might be also the case for binary black hole mergers. So here it says more or less one Lazzati Inferno, because I think this work wasn't focused on binary black holes, but I think it's perfectly plausible that you might be able to see what they thought mostly for short gamma ray bursts happening in AGN disks, also in this case of binary black holes, if there is a jet. So going to the case of GW190521, regardless of what we believe was the mechanism that produced the electromagnetic emission. We did some work also with Maya, trying to estimate what is the likelihood that we actually could have observed a flare of that kind in coincidence with the radiation wave event. So what we found for this specific event was that there was actually quite a high probability of chance coincidence, just because this event had a very, very large localization volume. It was probably, I think, the second to largest localization volume or something like that of the O3 catalog. And so that means there were a lot of AGNs in that volume, and AGNs vary a lot. And so it was not impossible to see a flare of that magnitude in coincidence with this event. But this motivated us to ask whether in the future, as we have a population of binary black holes and perhaps a population of flares, we could infer whether some fraction of these flares are actually connected with the binary black holes. With the main reasoning being, we'll probably never be able to say, at least until the localizations are what we have so far, we'll probably never be able to say this flare is associated with this binary black hole merger. But as a population, eventually, a background flares and associated flares will follow different distributions, also, for example, luminosity distance. So we should be able to discern between these two. And so our formalism is basically trying to constrain this parameter lambda, which is the fraction of binary black holes that give rise to AGN flares, or if you want to just consider AGNs in general, like an AGN catalog without considering the flares, you can take that lambda as a fraction of binary black holes that occur in AGNs. But in general, what we're trying to do is to find the signal AGN, the one that is actually related to the binary black hole merger, on top of some background AGN that may also be varying at the same time as the radiation wave event. So we did some simulations at the time that are now, I believe, probably too optimistic compared to what we currently have in terms of sensitivity in O4. So I would consider these more applicable these results more applicable for what we'll have in O5. But so the idea is that with the follow-up of the best events that we'll have in O5, eventually already in O4, and by best events, we mean the ones that will have a smaller background rate of AGN flares. So thinking the best localized ones, right, when you have less AGNs, but also the more massive ones where we believe that the flare might be more prominent. And so again, larger flares are rarer, so you have a smaller background. So focusing on these events, here we're asking the question: how many follow-up do we need to do in order to make in order to say whether lambda is larger than 0? It's not consistent with 0, so there is an association between the two. But obviously, that's a function of the true value of lambda, the true value of how many binary black holes are actually inducing AGN flares. And so what we find is that we can say, we can make a confident association within 1 year of about LBK running at design sensitivity, as long as this value of lambda is at least 10%. So this is this line here. So you need something like 10 events to follow up that are well localized and massive enough in order to make this association. So what did we do so far in terms of following up binary black holes? I mentioned earlier this event, S230922G. So we believe possibly, because we don't know from LIGO what the mass is, we just want to know this is somewhat massive, so we kind of do a back of the envelope estimate using just using the false alarm rate and the localization and the distance. The idea is that we want to select things that are at least 50 solar mass in total mass. So ideally, this is the mass distribution of this is the primary component in binary black hole system from GWGC3. The idea is that perhaps we want to get something that is past the peak at 30 solar masses, so something that might be in this regime where we believe that there could be a lot of hierarchical mergers happening. So we want something like a 40 solar mass plus a 10 solar mass black hole. It's something that you might expect to see in an AGN disk, so that's why we're selecting this total mass larger than 50 solar masses. And so we went through all of these candidates that we found in the localization volume, made all of our selections, followed that some, discovered that quite a few were supernovae in the region. And we found this specific one, I'm showing you here on the right, that seemed quite interesting, the only one that survives our cuts. So you see it's quite blue. This is GNI band observations. It rose by about 1 magnitude since the time of the gravitational event, and then started going down, maybe plateauing a little bit. We were able to take 2 spectra. As you see, these vertical lines, one with Keck, one with Gemini. Here you see the spectra on the bottom, but the interesting thing is these zoom-in panels. So we see some asymmetric broadline variability that could be indicative of an off-center source. So this is something that the models had predicted before. So this is a broad magnesium-2 and the broad H-alpha line. So if you look at the Keck spectra, the ones that are shown in blue, there seem to be some extra component on the red side of the line, and this seems to be disappearing in the later spectrum that we took with Gemini. We don't see that anymore. On the bottom, you see the residuals between the model from our feet, just a simple Gaussian, and the actual data. So this was, we found this very interesting, and hopefully the results from this will be out soon, but this is a candidate that we have so far. Hopefully taking another spectrum this year, we'll be able to say what's happening since then to the broad lines. So now, the last thing I want to mention.
Quick question about the AGN. So of course, if they were background players, then the first order thing you would expect is they have an equal number a week in advance as the week following the gravitational wave, right? So there. What other statistical tests do one do besides something simple like that?
Well, just doing, for example, a dump around the walk fit. So if one has a historical light curve of that object, or maybe one can go back and do it later, you can try to fit a dump around the walk, which is what people often use to describe the behavior of AGNs, and then try to see whether you can predict, you can fit that specific flare with the other behavior, stochastic behavior of the AGN. That would be an option to see whether it's consistent with the AGN history.
Typically, given the expected error ellipses, how many AGN would you be sampling for a given event?
That's a good question. I don't think I have a number also because these error regions can span like orders of magnitude. Yeah. But yeah, it can definitely go from, I think for the one that was really well localized, I think the number was like 40 AGNs that we had, or known AGNs at least, but it can go up to tens of thousands. Yeah. This one was decently localized for this run. So maybe the last, I'll just use one more minute to say that you can do some cosmology, with this flare. Obviously, you can say, okay, I know that that's the counterpart, so I use it as a bright standard siren. This is what people have done in different papers, at least for GW19 or 521. But what we suggested was that perhaps you can, use our formalism, the one that that I mentioned earlier, to constrain lambda, the number of events that give rise to AGN flares, and at the same time also measure cosmological parameters, with the idea being that you're taking into account the fact that you don't know that all of these flares are actually associated with the gravitational wave event. So here, yeah, we opened up to constraining lambda at H0. These events are, can be quite large distances, so one can imagine to open up even to other things like omega matter, or even the W, the Carnegie equation of state parameter. And so, although eventually, the parameter that we find we're able to constrain is mostly H0, just because most of the events that are really constraining are those that are at lower distances. And so we came up with these constraints that maybe I don't have time to go through in detail, but just to say that, obviously the expected H0 precision will depend again on the true value of lambda, what is the fraction of events that are actually occurring in AGNs, and this is as a function of the number of events that you combine. So for something like 1 year of running at the sign sensitivity that I don't know what that corresponds to anymore. Initially this could have been 0.04, but it's probably closer to 0.5. We can reach something that is between 3 to 8% in this range here for most of the values of lambda, between 10 and 30%. Some papers have shown that actually 20 to 80% of the entire binary black hole population might be originating in AGNs. So that's a possibility. The last thing I'll mention is that you don't need to use AGN flares to make this kind of measurement, but you can also just use AGN catalog. So it would be similar to the dark standard time method, but now you're only taking into account AGNs. And I will stop here and take any questions you might have. Thank you.
Yeah, we could be able to set limits for the cosmological constant.
Yeah, so if you're thinking about like omega lambda, yes, this is something that could be possible with the binary black hole case. But as I was mentioning earlier, we tried to open the parameter space also to something like the omega lambda, but because most of the events, at least in say LDK design sensitivity and A class, the ones with the better localizations are the ones that have a lower background noise, and sort of the ones that give us the better precision. They're all at kind of small distances. So yeah, for the most part, we're sensitive to H naught. So we can constrain also omega lambda, but to a worse precision from H naught.
Just a question of the BPH-AGN association when you don't see a flare. Presumably you have some model that's telling you what the probability of an association is. This is something that's coming from first principle astrophysics theory. Do you marginalize over model prediction somehow, or how does that work?
So you're saying if some binary black holes could have...
Yeah, I guess I'm curious, what is in the event where you're not associating with the flare, how do you determine the prior probability of the BPH being associated with an AGN formation environment specifically?
Yeah, so at the moment we did not, we're being agnostic in terms of that prior, but that's definitely something we should fold in, right? So like maybe if you have a model that gives you, population prediction that, and there are some that show that something like it starts around like 20 solar masses, like that's the mass distribution that you expect, and tails off at larger masses. That's definitely something that we should try folding. Yes, we haven't tried that. Good idea.
How good are AGN catalogs for these typical events? Like, do you know where the AGN are before you start the follow-up?
Yeah, so at the moment, one catalog that we've been using much more is the Gaia catalog. It comes from Gaia, so at least that's kind of uniform, as it has a magnitude limit of about, I think it's G 20.5 or something like that. So at least we know what we're looking at compared to other like milli-pos, like Franken catalogs that have a lot of different things. So I think we trust that catalog up to that magnitude limit. But yeah, we're missing out on dwarf AGNs, and I think that would be something that we need to start exploring. Like, what do we believe the contribution is coming from low luminosity AGNs to this channel? Like, there must be a point where you produce too many binary black holes to be consistent with the LIGO rates. And so maybe you should not open, to all of the low luminosity AGNs and the high luminosity RNO. So that's something that we should definitely start addressing. But for now, we're just using magnitude limited catalog.
And one basic aspect, of course, of galactic nuclei is they tend to be much more metal rich than other parts of galaxies, like flux clusters. And so, I mean, there's always the issue, well, your black holes, maybe they continue to accrete after you form them and so on. There also is a caveat associated with it, they can really do that. So if binary black hole mergers in AGN, that's of course systematically lower mass than those in cloud clusters. Presumably that would have a negative impact on the detectability. I mean, the rate could be significant, but if they're factor 3 lower mass, then don't they become much harder to detect?
Yeah, I don't know. I think that what at least I believe the theories that have done the calculations is that you are pretty good at retaining the things that previously merged. So maybe you need to go through like 3 mergers to produce the higher mass objects, but you can still do that. And with accretion, I don't know. You're not convinced.
Well, anyway, it's a rabbit hole. But perhaps to turn the question around, without the electromagnetic transient coincident with the merger, that somehow you could establish really was physically associated. Is there any way of saying, given what type of star cluster, say, with a nuclear versus a globular, that it's coming from? I mean, if the spins are, I understand you have a systematically high spin component. And that sounds like it might be the best spin. Would that be the case? I mean, just separating out different spin components in there.
From the BBH population, you're saying? I mean, I know that people have tried that, but as far as I can tell, with the AGN channel, you can produce like anti-line spins, and so like you can produce all sorts of things. So I think it's really hard to disentangle. At least that's my view as an observer. But maybe in the future, I don't know, it could be possible to do better. Yeah. I know that some people, at least for 190521, there's a group that claimed a highly eccentric orbit, and potentially that could be an extra suggestion that actually, yes, this could have happened in an AGN, or any way that it was a dynamical interaction that formed it. But yeah, maybe the LIGO people can tell me if they trust that kind of constraint that could give you some indication that originated in a dense environment.
I think the fraction of hierarchical mergers that you said very strongly correlated with the assumed speed of the environment.
Mm-hmm.
Yeah, it's a matter of principle, sure.
Yeah. So that you can distinguish like a nuclear star cluster or an AGN that would have a much higher assumed speed from a globular cluster.
So for your bright sirens like AGN measurement, if you find an associated flare, then you're assuming that it's from that galaxy specifically in your bright science version of this, right? Is that the case? I'm not sure I fully understand it.
Yeah, so my suggestion would be not to do that unless you're 100% sure that they are associated. Like maybe if you have something that's super well localized, like 1 square degree, and you have this AGN flaring by 1 magnitude, this super rare flare, at that point maybe I'll be like, yes, then at that point actually also our formalism becomes effectively a bright siren and should give consistent constraints.
Okay, and do you account for like the probability of an AGN flare in a given bit of observation?
Yeah.
And then I guess you just statistically weigh that
Exactly.
with like those sky map localization.
That's the idea.
Yeah, so I guess we can continue any other discussion upstairs with refreshments, but let's thank Antonella again.